This is the Acorn Archimedes, released in 1987. It was the first computer with an ARM processor that was commercially available to the general public. But this is just a photo of that computer in a browser, running on a Windows emulator, running on a phone with an ARM processor. Well, I'm running to tell you about this. The REDMAGIC 9S Pro, which contains the Snapdragon 8 Gen 3 leading version chipset. Currently the world's best mobile ARM processor on the market. I've been wanting to talk about the ARM architecture for a while now, especially since ARM chips have been coming all the way back around to the mainline PC market, what they were originally designed for. Still, I don't think REDMAGIC expected me to try to install Windows 11 and create the world's first Android game written in ARM assembly, but come on, you can't just expect me to not write just a little assembly code. But first, let's talk about the advanced reduced instruction set computer machine architecture that's been around for nearly just as long as x86 at this point. I'm sure at this point we all know the story by heart of how the original Acorn RISC machine CPU became highly regarded for its heritage and renewal projects, including the refurbishment of Hamer Hall at Arts Centre Melbourne. Wrong Wikipedia article there. Well, anyways, the moral of the story is that ARM is a RISC architecture, which means that it's super power efficient. Between dynamic voltage scaling, power gating, and optimized memory subsystems, it's really no wonder that these chips have such great performance at low power levels. Except that none of that has anything to do with the chip's instruction set architecture. Chips from Intel, AMD, and other companies also incorporate DVS power gating and optimized memory subsystems among the many other power optimizations in their own chips. It turns out that the reason ARM chips are so power efficient is because they're designed for low power devices like your phone, smartwatch, or mobile dog. It has nothing to do with having a RISC or CISC or BISC architecture. It's the implementation of the chip design that matters most, not the ISA. If you're still not convinced, there's a great article from Chips and Cheese on this that I'll link down below. And just for the record, Japan's Fugaku supercomputer based on the Fujitsu A64 FX ARM CPU draws much more power than the current world's fastest supercomputer, the Frontier, which runs on x86 CPUs. But of course, that doesn't mean that ARM chips like the Snapdragon 8 Gen 3 aren't more power efficient than ever. So what's the real difference between these two ISAs? Well, x86-64 CPUs have 16 general-purpose registers, while ARM64 CPUs on the other hand have 31 general-purpose registers. Yet at a basic level, x86 and ARM instructions do pretty much the same thing: calculations, logic, branching, reading and writing to and from memory. So maybe the most obvious difference here is that ARM is a load-store architecture. And while x86 has over the years expanded to include so many other complex instructions for SMID, cryptography, and virtualization support, at the same time the ARM instruction set has also expanded to support those same features. So I guess it's no surprise then that while x86-64 CPUs have a total instruction variant count of 3,684, ARM itself has somewhere in the ballpark of 1,300 or more instruction variants. It's really no surprise either that today's top-of-the-line smartphone SoCs outshine top-spec desktop CPUs from only a few years ago, well outdo the best Chromebooks currently on the market, and let's just say that I really hope that the Nintendo Switch Color has some serious hardware upgrades. In fact, do you even need a PC at all at this point? What exactly can you do on a PC that you can't do on a phone like the REDMAGIC 9S Pro? I mean, look at this, I can play Snake on the home screen. What does your desktop do? Of course, we won't get the feeling of a true PC experience without Big Brother Microsoft looking out for us. And although Windows is on ARM, it's just not possible to boot into Windows from a device like this, since there'd be no way to interact with it without the supporting drivers. But while Windows can't be experienced natively, there are some alternatives we can resort to for a Windows-like experience. There's direct emulation through the likes of QEMU, but while I was able to get Tiny11 to boot nearly all the way up, it failed close to the end of the process, and no matter what settings I changed, I was never quite able to make it go all the way there. Although apparently some people have had great success and adequate performance results emulating the Windows on ARM version of Windows 11. What works for me is the WinLater app, which allows the user to run Windows x86-64 programs through Wine, Box86, and Box64. In the app, I can simply create a new container and even specify what kind of GPU hardware to emulate. Then once running, we're not actually in Windows proper, but an environment that will let us run Windows x86-64 programs, like this one, or okay, not that one. Not every program will run, and I'm fairly sure there's only support for up to DirectX 9 here, so typing Simulator 3D using DirectX 11 is out of the question. But at least we have Minesweeper, Solitaire, a really slow version of Internet Explorer, and even Google Chrome as long as you don't care about JavaScript working at all. To be honest, trying to run x86 programs probably isn't worth it, and while you could just always remote into your desktop using Steam, the new Windows app, or whatever else, that kind of defeats the purpose of having such a powerful CPU on this device. There has been some recent news about Valve testing Proton support for ARM64, so there very well could come a day when a phone like this can just run PC games from Steam, since for many titles it's not a question of available computational power, but platform support. So while it's great to go off and play in the land of make-believe x86 Windows, at the end of the day, this is an ARM device and will get the best performance running programs built for ARM. So if we really want to use Chrome that badly, turns out there's an app for that. In fact, pretty much anything the average person wants to do on a PC, you can do on a phone nowadays. Considering that Google's Office apps are more popular than Microsoft's at this point, it may not be the craziest idea to get a portable monitor, keyboard, and mouse and ditch the e-waste. But I can't think of a better method to dive into the beating heart of the system and to get a good look at just what the ARM ISA can do than writing an app in ARM64 Assembly. I guess what I'm saying is that I'll basically do anything to avoid programming in Java. While it's possible to use pure assembly to write an app, getting any kind of GUI support won't be very easy. Luckily, a while ago I came across a video explaining how to write full Android apps in plain old C, and additionally they provided an associated graphics library. So through the magic of the compiler, I can also include an assembly file into the list of files to be wrapped up into the final app. And did you see how that compiled in like 2 seconds? That's so much better than the year and a half it takes through Android Studio. And having this separate assembly file is by far easier than having to rely on the clunky syntax and restrictions of inline assembly embedded in the C program. The way this app is designed, all the logic and data behind the game is run within the assembly code section of the program that outputs a 224 by 288 buffer that represents the game screen. This buffer is then taken and processed by the rest of the app's C code using the provided raw draw graphics library to output the game onto the device's screen. In fact, besides that, the only thing the C code is doing is determining the proper frame timing and reading the touchscreen input to determine the direction of the virtual joystick, which is then passed on to the assembly program to calculate the next frame of the game. You could almost think of this as a Pac-Man on a chip at the center of this program, since you could easily port this core assembly section over to any other ARM machine. Here's what it looks like when the game doesn't scale up the final output. In terms of the assembly code itself, I called upon all my experience of programming the NES and Game Boy to treat this game as if it was being written for an 8-bit machine. Pac-Man and the Ghost are all treated as sprites within associated X and Y location and character from the game's character ROM, and other game variables are all kept within the virtual 0 page of the machine. After going through the game's logic, the sprites are drawn on top of the background and then sent onto the output buffer. I won't lie, I'm not a huge fan of ARM assembly syntax. My assembly code certainly doesn't make use of hardly any complex tricks and techniques, but I do appreciate some useful features like adding a condition to an instruction. When copying sprites onto the output screen, I can first check if the pixel color is the background color of the character ROM, and if so, skip copying that pixel. This would have required a separate label and branching to do the same thing in another assembly language. For being the world's first ARM assembly mobile game, I don't think it turned out half bad, and if you'd be interested in seeing a deeper dive into the design of this game, just leave a comment down below. With ARM chips now coming back around to the desktop scene, it may be only a matter of time until the line between your PC and phone is blurred beyond recognition. Honestly, if I can fit an entire PC in the palm of my hand, I'm all the more grateful for that convenience. If you're interested in checking out this device for yourself, I'll leave a link to it down below. But wait, did you just say there's no titanium in this thing? Seriously? Oh, it's basically a paperweight at this point.